Hello, in this lecture I answer two questions. In the first question, you find out the area of this green shape using two different methods. And in the second question, you find out the radius of this semicircle that is described by rectangle ABCD. So let's start with the first question. So the following, we have rectangle ABCD. This is line segment AE, this equals to 1 unit in its length. Side AB of rectangle ABCD equals to 4 units in its length. Inside the rectangle we have this green shape. The green shape is actually triangle BEC. So we have to find out the area of this green triangle BEC. You also know that this angle BEC is equals to 45 degrees inside. Again, our task is to find out the area of this green shape. This is actually the green triangle BEC. So first of all, ABCD is rectangle, therefore all those four angles are right angles. And define the length of this line segment ED as x. So in total, AD equals to 1 plus x. We also know that the opposite sides of a rectangle are equal to each other. So in rectangle ABCD, side AB equals to the opposite side DC, but AB is 3, therefore the opposite side DC must be also equal to 3 units in its length. Likewise, according to the sum rule, in the sum rectangle ABCD, side AD equals to the opposite side BC. But AD equals to 1 plus x, therefore the opposite side BC must be also equal to 1 plus x units in its length. In the next step, we will do a construction. That is to say, from point E, we will do perpendicular on BC. Again, from point E, we will do perpendicular on side BC of rectangle ABCD. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees inside according to our construction. We define the touching point of the perpendicular from point E, and side BC, this point is point M. By doing this construction, we're going to do quadrilateral ABME. Inside quadrilateral ABME, we have 1, 2, 3 rectangles. The sum of 3 rectangles is 270 degrees, so 270 degrees plus the size of this fourth missing angle, total must be equal to 360 degrees. According to the rule that says that the sum of the angles in any quadrilateral is equal to 360 degrees. And therefore this fourth missing angle must be equal to 90 degrees in size. So inside quadrilateral ABEM we have 4 angles, and therefore can relate to quadrilateral ABEM as a rectangle. But you also know that the opposite sides of a rectangle are equal to each other. So in rectangle ABME, side AB must be equal to the opposite side EM. But AB is 3, therefore the opposite side EM must be also equal to 4 units in its length. So EM equals to 3. We define the perpendicular EM as h, so EM equals to h equals to 3. H equals to 3. So actually, h is the height to the base BC of the green triangle BEC. Okay, so in the next step, we will implement the Pythagoras theorem on this upper right triangle AEB. According to the Pythagoras theorem, In any right triangle, the score of the hypotenuse equals to the sum of the sides of the perpendiculars. Here by PT is the information for the theorem. So in this right triangle AEB, according to the Pythagoras theorem, BE squared, that is the square of the hypotenuse, equals to AE squared plus AB squared. And again, in this right upper triangle AEB, according to the Pythagoras theorem, BE squared equals to AE squared plus AB squared. The hypotenuse BE is the missing side, so we leave it as it is, so it is BE squared equals to AE squared. AE is 1, therefore AE squared is 1 squared, that is 1 plus AB squared. AB is 3, therefore AB squared is 3 squared, that is 9. So the total of the BE squared equals to 1 plus 9, that is 10. So BE squared equals to 10. Here we take a root out of this equation and find again that the missing hypotenuse BE is equal to the square of 10 units in its length. This is the hypotenuse BE that equals to the square of 10 units in its length. In the next step, we will implement the Pythagoras theorem on this lower right triangle, triangle EDC. In this lower right triangle EDC, according to the Pythagoras theorem, EC squared, that is the square of the hypotenuse, equals to ED squared plus DC squared. And again, according to the Pythagoras theorem, in this lower right triangle EDC, EC squared, that is the square of the hypotenuse, equals to ED squared plus DC squared. EC is the missing hypotenuse, so we leave it as it is, so it is EC squared equals to ED squared. ED squared, therefore ED equals to X, therefore ED squared is X squared plus DC squared. DC is 3, therefore DC squared is 3 squared, that is 9. So total we found out that EC squared equals to X squared plus 9. Here we take a root out of this equation and find again that the missing hypotenuse AC or the right triangle EDC is equal to the square root of X squared plus 9. In the next step, we calculate the area of the green shape, that is actually the area of this green triangle EBC by using two different methods. And then we create an equation that says that the area of this green triangle EBC according to the first method must be equal to the area of this green triangle EBC according to the second method. So we calculate the area of this triangle green triangle ABC according to the first method. You know that the area of any triangle equals to the base of the triangle times the height over 2. We'll choose the base of this green triangle ABC as BC times the height is h, over 2. In total, if we found out that the area of the green triangle ABC according to the first method of calculation is equal to BC times h over 2. We already found out that BC equals to x plus 1 times h is 3 over 2. So in total we found out that the area of this green triangle ABC according to the first method of calculation is equal to 3 times x plus 1 over 2. In the next step, we calculate the area of this green triangle ABC in a different way. Actually, this is triangle ABC that could be any triangle. The length of side AC of this triangle ABC is equal to 2 units. Side AB equals to A units in itself. This is angle theta, that is the angle between A and B. The area of this triangle ABC that could be any triangle equals to the multiplication of the two sides by each other. This is to say A times B times the angle between those two sides. This is theta over 2. And again, the area of this triangle ABC equals to A times B times sinus theta over 2. So the area of any triangle equals to the multiplication of the two sides by each other times sinus the angle between the two sides over 2. Okay, so according to the formula that I presented to you, the area of this triangle EBC according to the second method of calculation is equal to the multiplication of the two sides by each other, that is to say EB times EC times sinus the angle between the two sides, that is sinus 45 degrees over 2. And again, the area of this green triangle EBC according to the second method of calculation equal to the multiplication of the two sides by each other, that is to say BE times EC times sinus the angle between the two sides, that is 45 degrees over 2. This equation is the implementation of the new formula in our triangle EBC. So in the next step, we create the equation 3 that says that the area of triangle, the green triangle EBC according to the first method of calculation must be equal to the area of this green triangle EBC according to the second method of calculation. So according to equation 3 says that the area of the green triangle EBC according to the first method of calculation must be equal to the area of the same green triangle EBC according to the second method of calculation. So the area of the green triangle ABC according to the first method of calculation equals to 3 times x plus 1 over 2 square units in size. And this must be equal to the area of the same green triangle ABC according to the second method of calculation. The area of the green triangle ABC according to the second method of calculation equals to EB times EC times sinus 45 degrees over 2. So here we have 2 on both sides of this equation, equation 3, so 2 will get cancelled. After cancel 2, on this side of equation 3 we left only with 3 times x plus 1, and is equals to, on the other side of equation 3 we left with EB times EC times sinus 45 degrees over 2. But we already found out that EB equals to the square root of 10. So we substitute EB by square root of 10. And we already found out that EC in total equals to the square root of x squared plus 9. Therefore, we substitute EC was square root of x squared plus 9. Again, EC equals to the square root of x squared plus 9 times sinus 45 degrees. Sinus 45 degrees equals to the square root of 2 over 2. So in total, according to equation 3, we actually found out that 3 times x plus 1 equals to the square root of 10 times square root of x squared plus 9 times the square root of 2 over 2. The square root of 10 times the square root of 2 equals to the square root of 20. So write it down. So according to equation 3, we found out that 3 times x plus 1 equals to the square root of 10 times the square root of 2 is the square root of 20 times the square root of x squared plus 9 over 2. So in total, we should found out that according to equation 3, 3 times x plus 1 equals to, here we have square root of 20. We substitute 20 by 4 times 5, so inside the root we have 4 times 5 times the square root of x squared plus 9 over 2. So according to equation 3, we found out that 3 times x plus 1 equals the square root of 4 is 2, so we take 4 out of the root. So inside the root we left only the square root of 5, with 5. And we have times square root of x squared plus 9 divided by 2. So in this equation 3 we have 2 in the numerator and 2 in the denominator, so 2 will get cancelled. After we cancel 2, we have here according to equation 3, 3 times x plus 1 equals to the square root of 5 times the square root of x squared plus 9. Here we will square both sides of this equation, equation 3. We get that according to this equation, equation 3, we have 3 squared, that is 9, times x plus 1 squared, and it's equals to the square root of 5 squared is 5, and the square root of x squared plus 9 squared equals to x squared plus 9. Well, because of the fact that the square cancels the root, and we left only with x squared plus 9. So today we found out that 9 times x plus 1 squared equals to 5 times x squared plus 9. Here we will open the brackets on both sides of this equation, equation 3, and get that according to equation 3, 9 times x plus 1 squared. X plus 1 squared equals to x squared plus 1 squared, that is 9, plus 2 times x times 1, that is 2x, and it equals to 5 times x squared plus 9. 5 times x squared is 5x squared, and plus 5 times 9 is 45. So in total we found out that 9 times x squared plus 1 plus 2x equals to 5x squared plus 45. Here we will open the brackets on this side of this equation, equation 3, and we get that according to equation 3, we have 9 times x squared is 9x squared, plus 9 times 1 is 9, plus 9 times 2x is 18x, and it equals to 5x squared plus 49. So in total, we found out that according to equation 3, x squared plus 9 plus 18 squared equals to plus 18x equals to 5x squared plus 49. Here we subtract 5x squared from this equation, equation 3, and get that according to this equation, equation 3, 9x squared minus 5x squared equals to 4x squared plus 9 plus 18x, and it equals to 49. Here we subtract 49 from this equation, equation 3. So in this end of equation 3 we have 4x squared plus 18x, and 9 times 9, okay. Here we have it is 45, not 49. So it is plus 45. So here we subtract 45 from this equation, equation 3. Again, according to equation 3, we have, in this of equation 3, we have 4x squared plus 18x, and 9 minus 45 equals to 9 minus 45 equals to minus 36, and it equals to 0. Here we divide this equation, equation 3 by 4. Again, that's according to this equation, equation 3. 4x squared over 4 is x squared. (18x over 4 is 4.5x, and minus 36 over 4 is minus 9, and it equals to 0 over 4 is 0. So in total we found out that according to equation 3, x squared plus 4.5x minus 9 equals to 0. So this is the quadratic equation, and the general formula for a quadratic equation is as follows: ax squared plus bx plus c equals to 0. This general formula, a, b, and c are the coefficients of this quadratic equation. And x is the variable that we are looking for. And we find out the value of x according to the following formula. X equals to minus b plus minus square root of b squared minus 4 times a times c over 2a. In our specific quadratic equation, that is to say x squared plus 4.5x minus 9 equals to 0, the variable that we are looking for is x, and x is the length of this line segment ED. The coefficient A equals to 1, the coefficient B equals to 4.5, and the coefficient C equals to -9. So the only thing that is left to do in order to find out the variable that we are looking for with this x is just to put the data of our specific quadratic equation inside this general formula for x. This way we find out the value of the values of x, because x might have two solutions. So we do it now, we get that x equals to minus b. B is 4.5, therefore minus b is minus 4.5, plus minus the square root of b squared. B is 4.5, therefore b squared is 4.5 squared, this is 20.25, minus 4 times a times c. A is 1, so minus 4 times a is minus 4 times 1, that is minus 4 times c. C is minus 9, so minus 4 times minus 9 is plus 36. So in total, minus 4 times a times c is plus 36, divided by 2a. A is 1, so 2a is 2 times 1, that is 2. So in total, if we found out that x, that is the variable that we are looking for in our specific quadratic equation, is equal to minus 4.5 plus minus, inside the root we have 20.25 plus 36 equals to 56.25. So inside the root we have only 56.25 over 2. So if you found out that x equals to minus 4.5 plus minus the square root of 56.25 is 7.5 over 2. So in total, if we found out that x equals to minus 4.5 plus minus 7.5 over 2. So here we have two solutions that are possible for x. The first solution for x is as follows. X equals to minus 4.5 minus 7.5 over 2. Minus 4.5 minus 7.5 is minus 12 over 2. Minus 12 over 2 is minus 6. So according to the first solution for x, x equals to minus 6. But according to our definition, x is the length of line segment ED. So x is a length. So x is a length, it must be a positive number. Therefore, can never equal to minus 6, that is a negative number. So the first solution for x is incorrect solution, so we take into account only the other solution for x. The second solution for x is as follows. The second solution for x is x equals to minus 4.5 plus 7.5 over 2. So x equals to minus 4.5 plus 7.5 is 3 over 2. 3 over 2 is 3 halves, that is 1.5. So the second solution for x is that x equals to 1.5 units in its length. This is line segment ED equals to x, and x equals to 1.5 units in its length. Our task is to find out the area of this green shape, that is actually the green triangle EBC. So it is on. Our task is to find out the area of the green shape. The green shape is the green right triangle EBC. So our test is actually to find out the area of the green right triangle EBC. The area of this green triangle EBC equals to the base BC times the height edge over 2. So total, if you found out that the area of the green shape equals to the area of the green triangle BC, it is equals to the base BC times the height edge over 2. We already found out that BC equals, the base BC equals to x plus 1 times the height edge equals to 3 over 2. So in total, if you found out that the area that we are looking for in this question, that is the area of the green shape equals to x plus 1 times 3 over 2. X plus 1 times 3 over 2. X is 1.5, therefore x plus 1 is 1.5 plus 1, that is 2.5 times 3 over 2. 2.5 times 3 is 7.5 over 2. 7.5 over 2 is 3.75 square units in size. So if you found out that the area that we are looking for this question, that is the area of this green shape, in total it is equal to 3.75 square units in size. So we finish with the first method. In the next step I will present to you how to find out the area of this green shape according to the second method. Quadrilateral ABCD quadrilateral ABCD is a rectangle, and those four angles are all right angles. We define the length of this line segment ED as x. So in total, side AD equals to 1 plus x units in its length. We also know that the opposite sides of a rectangle are equal to each other. So in the rectangle ABCD, side AB equals to the opposite side DC, but AB is 3, therefore the opposite side DC must be also equal to 4 units in its length. Likewise, according to the sum rule, in the sum rectangle ABCD, side AD must be equal to the opposite side BC, but AD in total is 1 plus x, and therefore the opposite side BC must be also equal to 1 plus x units in its length. In the next step, we will do a construction, that is to say, from point E, we will do perpendicular on BC. Again, from point E, we will do perpendicular on side BC of this rectangle ABCD. So actually, this angle equals to 90 degrees in size, and this angle also equals to 90 degrees inside according to our construction. We will define the touching point of the perpendicular from point E and BC. This point is point M. By doing this construction, we can deduce the small quadrilateral ABME. Inside this small quadrilateral ABME, we have again all the inside rectangle are right angles. Inside rectangle ABC are right angles. So this is a right angle. This is also a right angle. And this is a right angle. So in the small quadrilateral ABME, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, so 270 degrees plus the size of this 4th angle. In total, it must be equal to 360 degrees. According to George, it said that the sum of the angles in any quadrilateral is equal to 360 degrees. And therefore, this 4th angle must be equal to 90 degrees in its size. So inside the small quadrilateral ABME, we have 4 right angles, and therefore we can relate to quadrilateral ABME as a rectangle. But we also know that the opposite sides of rectangle are equal to each other. So in rectangle ABME, side AB must be equal to the opposite side EM. But AB is 3, therefore the opposite side EM must be also equal to 3 units in its length. EM equals to 3. We define the perpendicular EM as H. This is the formation for height. So EM equals to H and H equals to 3. Therefore EM equals to H and H equals to 3. So H equals to 3 units in its length. H is the height to the base BC of the green triangle BEC. Again, H is the height to the base BC of the green triangle BCE. Okay. So we will define this angle AEB as theta. And we will focus on this right upper triangle AEB. On this right upper triangle AEB, triangle theta equals to AEB over AE. So write it down. The right triangle AEB, the right upper triangle AEB. Times theta equals to AB over AE. Repeat again, this right triangle AEB. Times theta equals to AB over AE. AB is 3 and AE is 1. So in total, we should find out that according to equation 1, times theta equals to 3 over 1, that is 3. So I can now, according to equation 1, tangent theta equals to 3. We have the algebraic identity, the trigonometric identity that states that tangent theta plus 45 degrees equals to 1 plus tangent theta over 1 minus tangent theta. So we will define this trigonometric identity as equation 2. We already found out that tangent theta equals to 3, so we can solve the tangent theta, this equation 2 by 3. We do it now, we get that in the numerator we have 1 plus tangent theta, that is 3. Well, in the denominator we have 1 minus tangent theta, that is actually 1 minus 3. 1 plus 3 is 4, over 1 minus 3 is minus 2, so 4 minus 2 is minus 2. So total, according to equation 2, we have found out that tangent theta plus 45 degrees equals to minus 2. So write it down. According to equation 2, we have found out that tangent theta plus 45 degrees is equal to minus 2. This is according to equation 2, and according to equation 1, we already found out that tangent theta equals to 3. This is side AD of rectangle ABCD. So AD is the side of a rectangle, it is absolutely a straight line. So if you focus on the right side of the straight line AD at point E, here the sum of the areas must be equal to 180 degrees according to rule 3. Rule 3 says that the sum of the areas on one side of a straight line is equal to 180 degrees. So write it down. If you focus on the straight line AD at point E, here the sum of the areas must be equal to 180 degrees according to rule 3. So which angles we have on the right side of the straight line AD at point E? This is angle theta, plus this angle equals to 45 degrees, plus this missing angle is actually angle DEC. In total, the sum of those three angles must be equal to 180 degrees according to rule 3. Repeat again. In the right side of the straight line AD at point E, the sum of the areas must be equal to 180 degrees. In the right side of the straight line AD at point E, the sum of the areas must be equal to 180 degrees. So which angles we have at the right side of the straight line AD at point E? We have angle theta plus the second angle, that is 45 degrees, plus the third angle, that is the missing angle, DEC. In total they must be equal to 180 degrees according to rule 3. So here we subtract from this equation theta plus 45 degrees, and finally we get the missing angle DEC. The missing angle DEC is equal to 180 degrees minus theta plus 45 degrees. This is the missing angle DEC. This is equal to 180 degrees minus theta plus 45 degrees. Write it down. and DEC equals to 180 degrees minus theta plus 45 degrees. In the next step, we focus on the lower right triangle, triangle EDC. In this lower right triangle, triangle EDC, tangents 180 degrees minus theta plus tangents 180 degrees minus theta plus 45 degrees equals to DC over ED. So write it down. This will be equation 3. So tangents 180 degrees minus theta plus 45 degrees equals to DC over ED. And again, in this right lower triangle, triangle EDC, tangents 180 degrees minus theta plus 45 degrees equals to DC over ED. DC is 3 over ED. ED is X. So in total, according to equation 3, we actually found out that tangents 180 degrees minus theta plus 45 degrees equals to 3 over X. So I'll copy equation 3 in a new page here. According to equation 3, we actually found out that tangents 180 degrees minus theta plus 45 degrees equals to 3 over X. We have another trigonometric identity that states that tangents 180 degrees minus theta equals to minus tangents theta. So according to this trigonometric identity, the value of this expression, that is to say, tangents 180 degrees minus theta plus 45 degrees according to this trigonometric identity, and the value of this expression is equal to minus tangents theta plus 45 degrees. Therefore, we substitute tangents 180 degrees minus theta plus 45 degrees by minus tangents theta plus 45 degrees because they are identical according to this trigonometric identity. So according to equation 3, we have tangents theta tangents 180 degrees minus theta plus 45 degrees equals to minus tangents theta plus 45 degrees, and it is equals to 3 over X. But again, according to equation 3, we actually found out that minus tangents theta plus 45 degrees equals to 3 over X. But according to equation 2, we have already found out that tangents theta plus 45 degrees equals to minus 2. So we substitute tangents theta plus 45 degrees in this equation 3 by minus 2. So in this equation 3 we have minus, I'll copy the minus here, and tangents theta plus 45 degrees, this expression equals to minus 2. So in total, this is our equation we have minus 2, this is equals to 3 over x. Minus times minus is plus. So minus 2 is plus 2. So according to equation 3, we actually found out that minus 2 is plus 2. And it is equals to 3 over x. Here we will multiply this equation 3 by x. And finally get this according to this equation 3. 2x equals to 3. Here we divide this equation 3 by 2. And finally get this according to this equation 3. X equals to 3 halves. 3 halves is 1.5. So x equals to 1.5 units in its length. This is line 17 D, is equals to x, and it is equals to 1.5 units in its length. Our test is to find out the area of this green shape. This is actually the green rectangle ABC. So our task is to find out the area of the green shape. The green shape, it is actually the green rectangle ABC. So our task is to find out the area of the green rectangle ABC. The area of this green rectangle ABC equals the area of this green rectangle ABC equals to the base BC times the height edge over 2. And again, the area of the green triangle ABC, this is actually also the area of the green shape, equals to the base BC times the height edge over 2. The base BC equals to 1 plus x times the height edge, that is 3 over 2. So now we found out that the area of the green shape equals to 3 times 1 plus x over 2. X is 1.5. X equals to 1.5 units in its length. Therefore, 1 plus x is 1.5 plus 1, that is 2.5. Again, 1 plus x is 2.5 times 3 over 2. 2.5 times 3 is 7.5 over 2. 7.5 over 2 is 3.75 square units in size. So the area of the green shape, that is the area that we are looking for in this question. In total, it is equals to 3.75 square units in size. So in both methods, we found out that the area of this green shape, that is the area that we are looking for in this question, it is equal to 3.75 square units in size. So we finish with the first question. In the next step, I present you the second question, and we solve the second question of this lecture. In the second question, our task is to find out the radius of this semicircle that is described by this rectangle ABCD. We know that this is the small line segment QB, is equals to 1 unit in its length. This is line segment PD, is equals to 2 units in its length. Again, ABCD is a rectangle. And our task is to find out the radius of this semicircle that is inscribed by this rectangle ABCD. So first of all the angles inside rectangle ABCD are right angles. So those 4 angles are all right angles. So this is the right angle. This is also a right angle. This is a right angle. And this is also a right angle. In the next step, we will define the point of tendency of tangent DC with this semicircle. This point is point M. Likewise, we will define the point of tendency of tangent BC with this semicircle. This point C. We will define the center of this semicircle. This point is point O. And we will define the radius of this semicircle as X. In the next step, we will join points O and M together by a straight line. Point O is the center of this semicircle, point M is the point of the semicircle itself, therefore OM is the radius of this semicircle, that is equals to X according to our definition. The radius OM that is equals to X, the radius OM is drawn to point M, that is the point of tendency of tangent DC with this semicircle. And whenever your radius is drawn to the point of tendency, then tangent DC will be perpendicular to the radius MO. If this is perpendicular to MO, it means that this angle equals to 90 degrees in size, and this angle also equals to 90 degrees in size according to rule 1. Likewise, we will join points O and T together by a straight line. Point O is the center of this semicircle, point T is the point of the semicircle itself, therefore OT is the radius of this semicircle, that is equals to X. Again, the radius OT is equals to X, the radius OT is drawn to point T, that is the point of tendency of tangent BC with this semicircle. Whenever your radius is drawn to the point of tendency, then tangent BC will be perpendicular to the radius TO. If BC is perpendicular to TO, it means that this angle equals to 90 degrees in size, and this angle also equals to 90 degrees in size according to the sum rule, rule 1. By doing this construction, we get the lower quadrilateral OTCM. Inside this lower quadrilateral OTCM, we have 1, 2, 3 rectangles. The sum of 3 rectangles is 270 degrees, so 270 degrees plus the size of this fourth missing angle, the total must be equal to 360 degrees, according to the rule that said that the sum of the angles in any quadrilateral is equal to 360 degrees. And therefore this fourth missing angle must be equal to 90 degrees in its size. So inside this lower quadrilateral OTCM, we have 4 rectangles, and therefore can relate to this quadrilateral OTCM as a rectangle. But you also know that the opposite sides of a rectangle are equal to each other. So in the lower rectangle OTCM, side OT must be equal to the opposite side MC. But OT is X, therefore the opposite side MC must be also equal to X units in its length. Likewise, according to the sum rule, in the same rectangle OTCM, side OM must be equal to the opposite side TC. But OM is X, therefore the opposite side TC must be also equal to X units in its length. So we found out that quadrilateral OTCM is not a rectangle but a square. Why? Because all of its sides are equal to each other, each side equals to X. So if you note, this is the small quadrilateral OTCM, that is a square. In the next step, we will do a construction, that is to say from point O, that is the center of this semicircle, we will do perpendicular on AB. Again, from point O, we will do perpendicular on side AB of this rectangle, ABCD. So actually, this angle equals to 90 degrees inside, and this angle also equals to 90 degrees inside according to our construction. We define the touching point of the perpendicular from point O and AB. This point is point L. By doing this construction, we can deduce the small quadrilateral LOTB. Inside this small quadrilateral LBTO, we have 1, 2, 3 degrees, and therefore this fourth missile must be equal to 90 degrees inside according to the sum rule. That says that the sum of the angles in any quadrilateral is equal to 360 degrees. And therefore inside quadrilateral LBTO we have 4 degrees, and therefore we can relate to this quadrilateral LBTO as a rectangle. Moving on. This is the upper quadrilateral LOTB. This is a rectangle because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle LBTO, side OT must be equal to the opposite side LB. But OT is x, therefore the opposite side LB must be also equal to x units in its length. This is side LB. Is equal to x units in its length. What is the length of this line segment LQ? From the drawing, it is very easy to see that LQ in total equals to LB minus QB. So it is not the missing line segment LQ is equal to LB minus QB. So the missing line segment LQ equals to LB, that is x, minus QB, that is 1. So total we found out that this is the missing line segment LQ. This is equals to x minus 1 units in its length. In the next step, we will do another construction, that is to say, from point O, that is the center of this semicircle, we will do perpendicular on AD. Again, from point O, we will do perpendicular on side AD of rectangle ABCD. So actually, this angle equals to 90 degrees inside, and this angle also equals to 90 degrees inside according to the construction. We define the touching point of the perpendicular from point O and AD. This point is point Z. By doing this construction, we can get quadrilateral LOZ. Inside this quadrilateral LOZA, we have 1, 2, 3 degrees, and therefore this fourth missing must be equal to 90 degrees inside according to the sum rule. It said that the sum of the angles in any quadrilateral is equal to 360 degrees. Quadrilateral LOZ is 4 degrees, and therefore we can relate to quadrilateral LOZ as a rectangle. By doing this construction, we created another quadrilateral. This is the lower quadrilateral OZDM. So in this lower quadrilateral OZDM, we have 1, 2, 3 degrees, and therefore this fourth missing must be equal to 90 degrees in size. So in quadrilateral OZDM we have 4 degrees, and therefore we can relate to this quadrilateral OZDM as a rectangle. But you also know that the opposite sides of a rectangle are equal to each other. So in this lower rectangle OZDM, side OM must be equal to the opposite side ZD. But OM is x, therefore the opposite side ZD must be also equal to x units in its length. What is the length of this piece in line 7? Line 7 ZP. From the drawing it is very easy to see that ZP in total equals to ZD minus PD. Again, ZP equals to ZD minus PD. So right now, let me say line 7 ZP. Is equal to ZD minus PD. So in total ZP equals to ZD, that is x, minus PD, that is 2. So total, the missing answer ZP equals to x minus 2 units in its length. This is angle ZOT. Angle ZOT, this angle equals to 90 degrees plus 90 degrees, that is 180 degrees. So write it down. The big angle ZOT equals to 180 degrees in its size. We know that any angle that equals to 180 degrees in its size, it is defined as a straight line. That is to say, line 7 ZOT is a straight line. Line 7 ZOT is a straight line. If line 7 ZOT is a straight line, it means that ZT is also a straight line. ZT is a straight line. If ZT is a straight line, it means that this is shape ABTZ that has 4 sides. 1, 2, 3, 4. So I did not shape ABTZ has 4 sides. And therefore shape ABTZ must be a quadrilateral. Shape ABTZ is a quadrilateral because it has 4 sides. So actually this is quadrilateral ABTZ. In this quadrilateral ABTZ we have 1, 2, 3, 4 right angles. Quadrilateral ABTZ has 4 right angles. And according to rule 5, any quadrilateral that has 4 right angles must be a rectangle, not a square. So we relate to this quadrilateral ABTZ as a rectangle. Quadrilateral ABTZ is a rectangle because it has 4 right angles. But we also know that the opposite sides of a rectangle are parallel to each other. So in this rectangle ABTZ, side AB is parallel to the opposite side ZT. AB is parallel to ZT. Okay. So AB is parallel to ZT, so we can implement here rule 10. We have side AB, this is parallel to side ZT. Line segment QP is the transversal. AB is parallel to ZT and QP is the transversal. That is to say it cuts the two parallels AB and ZT at those 2 points. So we can implement here rule 10. And please click on rule 10. Please click on rule 10. According to rule 10, corresponding angles between parallel lines are equal to each other. In the drawing, we have line A that is parallel to line C. The red line C is the transversal. That is to say it cuts those two parallels A and B, those 2 points. So those two angles are defined as corresponding angles and are located between the parallels A and B, therefore they must be equal to each other in their sizes. So if the size of this angle is 1, then the size of this angle must be equal to 1 according to this rule 2. Likewise, those two angles are also defined as corresponding angles and they are located between the parallels A and B. Therefore, they must be equal to each other in their sizes. So if you define the size of this angle as 2, then the size of this angle must be also equal to 2 because they are equal to each other according to this rule 10. So according to rule 10, corresponding angles between parallels are equal to each other. So we can actually implement rule 10 in our drawing. Why? Because in our drawing, line AB is parallel to ZT, QP is the transversal. This is to say it cuts those two parallels at those 2 points, Q and O. So all the requirements of rule 10 are satisfied, and therefore we can implement here rule 10. According to rule 10, those two angles are defined as corresponding angles and are located between the parallels AB and ZT. Therefore they must be equal to each other in their sizes. So if the size of this angle is alpha, then the size of this angle must be also equal to alpha because they are equal to each other. According to rule 10, it says that corresponding angles between parallels are equal to each other. Okay, so in this upper right triangle LQO, this angle equals to alpha, this angle equals to 90 degrees, and therefore this third missing angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees is equals to 180 degrees, that is the sum of the angles in a triangle. Likewise, in this lower right triangle OZP, this angle equals to alpha, this angle equals to 90 degrees, and therefore this third missing angle must be equal to 90 degrees minus alpha according to the sum rule that says that the sum of the angles in a triangle is equal to 180 degrees. In the next step, we prove that this is the right triangle LQO. We prove that this right triangle LQO can go into this right lower triangle ZPO according to side angle rule. So we have to prove that this is the green upper right triangle LQO. This right triangle LQO can go into this right triangle ZOP according to angle side angle rule. But before that, what is the definition of line segment OQ? Line segment OQ starts from point O, that is the center of the semicircle, and ends at point Q, that is the point of the semicircle itself. So this is exactly the definition of a radius. Therefore, OQ is the radius of this semicircle, that is equal to x units in its length. Likewise, what is the definition of line segment OP? Line segment OP starts from point O, that is the center of the semicircle, and then at point P, that is the point of the semicircle itself. Therefore, OP is the radius of this semicircle, is equal to x. So, while those two right triangles can go into each other. First of all, those two angles are both equal to alpha, and therefore they are equal to each other. This is angle LQO in the right triangle, LOQ, and it is equal to this angle. This is actually angle ZOP in the green right triangle, ZPO. It again, angle LQO in the right upper green triangle LQO equals to angle ZOP in the right lower triangle ZOP. They are both equal to alpha, and therefore they are equal to each other. In addition, side QO of this upper green triangle LQO is equal to side OP of this green lower triangle ZOP. They are both the area of the semicircle. That is equal to x, and therefore they are equal to each other. So write it down. QO equals to OP. This again, side QO of the green right upper triangle LQO is equal to side OP of the green right lower triangle ZOP. They are both equal to x, that is the area of the semicircle, and therefore they are equal to each other. Now the area of the semicircle that is equals to x, and therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees one alpha, and therefore they are equal to each other. So here this is angle LOQ. Of this green upper right triangle LQO, and it is equal to this angle. This is actually angle OPZ. On this green right lower triangle POZ. Then again, I should find out that angle LOQ of the right green triangle LQO equals to angle OPZ of the right lower triangle ZOP. They are both equal to 90 degrees one alpha, and therefore they are equal to each other. So I should prove that those two right green triangles can go into each other according to angle side angle rule. So right now, if you found out that the right upper green triangle LQO congruent, this is the sum congruent, to the right lower triangle ZOP according to angle side angle rule. This is to say, if you found out that those two angles and the side that is included between those two angles, that is side QO, this upper right green triangle LQO corresponding equal to those two angles, and the side that is included between those two angles, that is side PO of this green right lower triangle ZOP. And therefore those two green right triangles can go into each other according to angle side angle rule. We have those two angles, and the side that is included between those two angles, that is side QO of this green upper right triangle LQO corresponding equal to those two angles, and the side that is included between those two angles, that is side OP of this right green triangle ZOP. And therefore those two right green triangles can go into each other according to angle side angle rule. And from the fact that those two right triangles can go into each other, we will derive that the corresponding sides must be also equal to each other in their lengths. According to the rule that corresponding sides and congruent triangles are equal to each other. Those two triangles can go into each other, and therefore their corresponding sides must be also equal to each other in their lengths. The corresponding side of LQ is ZO. Why? Because both sides are located in front of this angle, that is 90 degrees one alpha. And therefore those two sides are defined as corresponding sides, and therefore they are equal to each other in their lengths. So LQ equals to ZO. LQ of upper green right triangle equals to ZO of the right green lower triangle. According to those, the corresponding angles of congruent triangles are equal to each other and the length. The corresponding sides in congruent triangles are equal to each other. Those are equal to each other. Those two green triangles congruent to each other, and therefore the corresponding sides must be equal to each other and the length. That is to say, LQ equals to ZO. But we already found out that LQ equals to x plus 1, to x minus 1. So we can write here that LQ equals to x minus 1. And from this equation, x minus 1 equals to LQ equals to ZO. We will have that ZO must be also equal to x minus 1 units in its length. This is side ZO, this equals to x minus 1 units in its length. We already found out that ZP equals to x minus 2, and the hypotenuse PO of this green right triangle OZP equals to x units in its length. So in the next step, we will implement the Pythagoras theorem on this right green lower triangle, triangle POZ. Here by PT is information for Pythagoras theorem. This green right lower triangle POZ, according to the Pythagoras theorem, OP squared, that is the square of the hypotenuse, equals to ZP squared plus ZO squared. But again, this green right triangle POZ, according to the Pythagoras theorem, OP squared, that is the square of the hypotenuse, equals to ZP squared plus ZO squared. OP equals to x, therefore OP squared is x squared. And it is equal to ZP squared. ZP is x minus 2, therefore ZP squared is x minus 2 squared. Plus ZO squared. ZO is x minus 1, therefore ZO squared is x minus 1 squared. So today we found out that x squared equals to x minus 2 squared plus x minus 1 squared. So here we will open the brackets of this side, of this equation, and we get that x squared equals to x minus 2 squared. X minus 2 squared equals to x squared plus 2 squared, that is 4, minus 2 times x times 2, that is minus 4x, plus x minus 1 squared. X minus 1 squared equals to x squared and plus 1 squared, that is 1, minus 2 times x times 1, that is minus 2x. So here we have x squared on both sides of this equation, so x squared gets cancelled. After we cancel x squared on this side of the equation, we are left with nothing, that is to say 0, while on the other side of this equation we have 4 plus 1 is 5, minus 4x minus 2x is minus 6x, plus x squared equals to 0. So if you found out that x squared minus 6x plus 5 equals to 0. This is the quadratic equation, and the general formula for a quadratic equation is as follows. Ax squared plus bx plus c equals to 0. This general formula, a, b, and c are defined as the coefficients of this quadratic equation, and x is the variable that we are looking for. And we find out the value of x according to the following formula. x equals to minus b plus minus square root of b squared on 4 times a times c over 2a. In our specific quadratic equation, that is to say x squared minus 6x plus 5 equals to 0, the variable that we are looking for is x. X is the radius of this semicircle. As you know, we are looking for the radius of the semicircle. This is x. Now specific quadratic equation. The coefficient a equals to 1, the coefficient b equals to minus 6, and the coefficient c equals to 5. So the only thing that is left to do in order to find out the variable that we are looking for in our specific quadratic equation, that is x, and x is the radius of the semicircle, is to put the data of our specific quadratic equation inside this general formula for x. In this way we find out the value of the radius of x, because x might have two solutions. And x is the radius of the semicircle. That is the radius that we're looking for in this question. So we do it now, we get that x equals to minus b. b is minus 6, therefore minus b is minus 6, that is plus 6, plus minus square root of b squared. b is minus 6, so b squared is minus 6 squared, that is 36, minus 4 times a times c. So it is minus 4 times a. A is also minus 4 times 1 is minus 4 times c. c is 5, so minus 4 times 5 is minus 20. So in total, minus 4ac equals to minus 20. So inside the root we have 36 minus 20 over 2a. a is 1, so 2a is 2 times 1, that is 2. So in total we found out that x equals to 6 plus minus square root of 36 minus 20 over 2. So x equals to 6 plus minus, inside the root we have 36 minus 20, that is 16, so inside the root we have only 16 over 2. So in total we found out that x, that is the value that we are looking for, that is the radius of the semicircle, equals to 6 plus minus, the square root of 16 over 4 is 4, so x equals to 6 plus minus 4 over 2. So here we have two solutions that are possible for x. The first solution for x is that x equals to 6 plus 4 over 10. 6 plus 4 is 10. Again, x equals to 6 plus 4 over 2. 6 plus 4 is 10, and 10 over 2 is 5. So the first solution for x is that x equals to 5 units in its term. We have another solution for x. The other solution for x is as follows. X equals to 6 minus 4 over 2. 6 minus 4 is 2, and 2 over 2 is 1. So the second solution for x is that x equals to 1 unit in its term. That is to say, the radius of this semicircle x equals to 1 unit in its term. We already found out that zp, line segment zp equals to x minus 2 units in its term. So write it down. Line segment zp equals to x minus 2 units in its term. If x equals to 5, then zp equals to 5 minus 2, that is 3. So zp is a length, and zp is definitely could be equal to 3. But what about 1? If x equals to 1, then zp equals to x minus 2. Zp equals to x minus 2, so it is 1 minus 2, that is minus 1. So we found out that zp is a negative number. But zp is a length, and zp is a length, it must be a positive number. Therefore, zp can never be equal to minus 1, that is a negative number. Due to the contradiction, we conclude that x can never be equal to 1, because we got to a contradiction. Another reason that zp can never be equal to 1 is because of the fact that zp is a length, so zp is a length, it must be a positive number. That is to say, zp is equal to x minus 2 must be a positive number. What is a positive number? It means that it must be greater than 0. So we have the inequality that says that x minus 2 must be greater than 0. We will add 2 to this inequality, and we get that x must be greater than 2. If x must be greater than 2, x can never be equal to 1 that is less than 2. So we have two reasons that x cannot be equal to 1. Therefore, the only answer to this question is that x equals to 5. So x, that is the radius of the semicircle, equals to 5 units in its length. Repeat again. The radius of this semicircle, that is the radius that we are looking for in this question, is equals to 5 units in its length. Okay, so we finished to answer the second question. In the next step, as well as the lecture, we start with the repetition of the second answer of the first question. Then we repeat on the solution of this second question. In the first question, our task is to find out the area of this ring shape. So, in the drawing, we have rectangle ABCD. This is line side AE, this equals to 1 unit in its length. Side AB of rectangle ABCD equals to 4 units in its length. Inside this rectangle ABCD, we have this green shape. The green shape is actually the green triangle BEC. This is angle BEC, this equals to 45 degrees inside. Again, our test is to find out the area of this. Our test is to find out the area of this green shape. This is actually the area of the green triangle BEC. So first of all, it is given as a question that ABCD is a rectangle. Therefore, all those four angles are right angles. We define the length of this line segment ED is x. So in total, AD equals to 1 plus x. And we also know that the opposite sides of a rectangle are equal to each other. So in rectangle ABCD, side AB equals to the opposite side DC. But AB is 3, therefore the opposite side DC must also equal to 4 units in its length. Likewise, according to the symbol, in the same rectangle ABCD, side AD must be equal to the opposite side BC. But AD in total is 1 plus x, and therefore the opposite side BC must be also equal to 1 plus x units in its length. In the next step, we did a construction. That is to say, from point E, we draw perpendicular on BC. Here from point E, we draw perpendicular on side BC of rectangle ABCD. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point E and BC. This point is point M. By doing this construction, we get the quadrilateral AB and E. Inside this quadrilateral AB and E, we have 1, 2, 3 rectangles. The sum of 3 rectangles is 270 degrees, so 270 degrees plus the size of this 4 pieces, and total must be equal to 360 degrees, according to the rule that says that the sum of the angles in any quadrilateral is equal to 360 degrees. And therefore, this 4 pieces must be equal to 90 degrees in size. So inside this one quadrilateral AB and E, we have 4 rectangles, and therefore can relate to this quadrilateral AB and E is a rectangle. So in rectangle AB and E, side AB must be equal to the opposite side EM. But AB is 3, therefore the opposite side EM must be also equal to 4 units in its length. We define the length of EM, perpendicular EM is x, therefore EM equals to h equals to 3, or h equals to 3. In the next step, we implement the Pythagoras theorem on this right upper triangle ABE. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So in this right triangle AB, according to the Pythagoras theorem, BE squared. In this right triangle AB, according to the Pythagoras theorem, BE squared, that is the square of the hypotenuse, equals to AE squared plus AB squared. Repeat again, this upper right triangle ABE, according to the Pythagoras theorem, BE squared, that is the square of the hypotenuse, equals to AE squared plus AB squared. BE is the missing hypotenuse, so we leave it as it is, and it equals to AE squared. A is 1, so A squared is 1 squared, that is 1, plus AB squared. AB is 3, so AB squared is 3 squared, that is 9. So in total, we found out that BE squared equals to 1 plus 9, that is 10. So BE squared equals to 10. Here we took out of this equation, and we found out that the missing hypotenuse BE equals to the square root of 10 units in its length. This is the hypotenuse BE, this equals to the square root of 10 units in its length. The next step, we implemented the Pandorus theorem on this right lower triangle EDC. According to the Pandorus theorem, in this right lower triangle EDC, EC squared, that is the square of the hypotenuse, equals to ED squared plus DC squared. Repeat again, this right lower triangle EDC, EC squared, that is the square of the hypotenuse, equals to ED squared plus DC squared. EC is the missing hypotenuse, so we leave it as it is, and it's equals to ED squared. ED is x, therefore ED squared is x squared plus DC squared. DC is 3, therefore DC squared is 3 squared, that is 9. So in total, we found out that EC squared equals to x squared plus 9. Here we took out of the equation, and we found out that the missing hypotenuse EC equals to the square root of x squared plus 9. Okay, again, this is the missing hypotenuse EC. With the triangle EDC is equals to the square root of x squared plus 9 units in its length. In the next step, we calculated the area of this green shape, that is actually the area of the green triangle BEC, in two different methods, and then we get the equation 3 that says that the area of this green triangle in BEM according to the first method of calculation must be equal to the area of this same right green triangle EBC according to the second method of calculation. According to the first method of calculation, the area of this green right triangle EBC equals to the base BC times the height edge over 2. And again, the area of this green triangle EBC according to the first method of calculation equals to the base times the height over 2. We choose the base as BC, the height is edge over 2. So in total, we found out that the area of the green right triangle BEC equals to the base BC times the height edge over 2. We only found out that the base BC equals to x plus 1 and the height edge is 3. And again, BC, the base BC equals to x plus 1 and the height edge is 3 divided by 2. So in total, we found out that the area of the green right triangle BEC according to the first method of calculation equals to 3 times x plus 1 over 2. In the next step, we calculated the area of this green triangle EBM in a different way. This is triangle ABC, that could be any triangle. The length of side AC is B, side AB equals to A units in its length. The area of this triangle ABC, that could be any triangle, equals to the multiplication of those two sides by each other, that is to say A times B times the angle between those two sides, that is theta, times sinus angle between those two sides, that is theta over 2. But again, the area of this green right triangle ABC, that could be any triangle, equals to A times B times sinus theta over 2. So we can implement the new formula in order to find out the area of this green right triangle BEC. According to the formula, the area of this right green triangle BEC equals to BE times EC times sin 45 degrees over 2. And again, according to the second method of calculation, the area of this green triangle BEC in total is equals to side EB times side EC times sinus angle between the two sides, that is 45 degrees over 2. This equation is the implementation of the new formula on our green triangle ABC. The next step, we created the equation 3 that says that the area of the green triangle ABC according to the first method of calculation must be equal to the area of the same green triangle ABC according to the second method of calculation. the area of the green triangle ABC according to the first method of calculation equals to 3 times x plus 1 over 2. And it must be equal to the area of the same green triangle ABC according to the second method of calculation is equals to EB times AC times 145 degrees over 2. So here we have 2 on both sides of this equation, so 2 will get cancelled. After cancelled 2 on this side of the equation, 3 we left only 3 times x plus 1, and on the other side of the equation we have EB square root of 10 times EC square root of equals to the square root of x squared plus 9 times sin 45 degrees. Sin 45 degrees equals to square root of 2 over 2. So total according to equation 3, we should find out that 3 times x plus 1 equals to the square root of 10 times the square root of x squared plus 9 over square root of 2 over 2. The square root of 10 times square root of 2 is square root of 20. So 3 times x plus 1 equals to square root of 10 times square root of 2 is square root of 20. Square root of 10 times square root of 2 is square root of 20 times square root of x squared plus 9 over 2. We substitute 20 by 4 times 5. So in total we should find out that 3 times x plus 1 equals to the square root of 20 is 4.5 times square root of x squared plus 9 over 2. Square root of 4 is 2, so we took 4 out of the root. Inside the root we left only with 5. So in total we should find out that 3 times x plus 1 equals to the square root of 4 is 2, so inside the root we left only with 5 times square root of x squared plus 9 over 2. Here we have 2 in the numerator, 2 in the denominator, 2 we get cancelled, so in total we should find out that 3 times x plus 1 equals to the square root of 5 times the square root of x squared plus 9. Here we have 3 times x plus 1. Okay, so here actually squared both sides of this equation, equation 3. We should find out that 3 squared is 9 times x plus 1 squared equals to the square root of 5 squared is 5 times the square root of x squared plus 9 equals to x squared plus 9. Why? Because of the fact that the square cancels the root and we left only with x squared plus 9. So total according to equation 3, we should find out that 9 times x plus 1 squared equals to 5 times x squared plus 9. So it is 9 times x plus 1 squared. X plus 1 squared equals to x squared plus 1 squared is 1 plus 2 times x times 1 that is 2x and is equals to 5 times x squared that is 5x squared plus 5 times 9 that is 45. So in total we should know that according to equation 3, 9 times x squared plus 1 plus 2x equals to 5x squared plus 45. Here we open the bracket on this side of this equation 3 and we found out that 9x squared plus 9 plus 18x equals to 5x squared plus 45. Again, in total we found out that after we open the brackets, we found out that according to equation 3, 9x squared plus 9 plus 18x equals to 5x squared plus 45. If we substitute 5x squared for this equation, we found out that 9x squared minus 5x squared is 4x squared, and we have plus 9 plus 18 squared equals to 5x squared plus 45. So 5x squared minus 5x squared is 0, so we left only 45. So in total, according to equation 3, we found out that 4x squared plus 9 plus 18x equals to 45. Here we substitute 45 for this equation, and we found out that 4x squared plus 18x and 9 minus 45 is minus 36 equals to 0. Here we divided this equation 3 by 4, and we found out that 4x squared over 4 is x squared, and 18x over 4 is 4.5x. Again, 18x over 4 is 4.5x. Minus 36 over 4 is minus 9 equals to 0 over 4 is 0. So in total we found out that x squared plus 4.5x minus 9 equals to 0. So this is a quadratic equation, and the general formula for a quadratic equation is as follows. Ax squared plus bx plus c equals to 0. This general formula, a, b, and c are the coefficients of this quadratic equation, and x is the variable that we are looking for. And we find out the value of x according to the following formula. X equals to minus b plus minus square root of b squared minus 4 times a times c over 2a. Now, specific quadratic equation, that is to say x squared plus 4.5x minus 9 equals to 0, the variable that we are looking for is x. X is the length of this transparent ED. the coefficient A equals to 1, the coefficient B equals to 4.5, and the coefficient C equals to minus 9. So the only thing that is left to do is to put the data of how specific coordinate equation inside this general formula for x. This way we find out the value of the values of x. So the left of line 7 ED, the left to x. So we did it and we actually found out that x equals to minus b. B is 4.5, therefore minus b is minus 4.5 plus minus square root of b squared. B is 4.5, therefore b squared is 4.5 squared, that is 20.25. Minus 4 times a times c. So it is minus 4 times a is minus 4 times 1 is minus 4 times c. C is minus 9, so minus 4 times minus 9 is plus 36. So in total, minus 4 times AC is plus 36. So inside the root we have 20.25 plus 36 over 2a. A is 1, so 2 is 2 times 1, that is 2. So in total, we should find out that x equals to minus 4.5 plus minus, and again, 20.25 plus 36 equals to 56.25 divided by 2. The score to 56.25 is 7.5. So in total, we should find out that x equals to minus 4.5 plus minus 7.5 over 2. So here we have two solutions that are possible for x. The first solution for x is as follows. X equals to minus 4.5 minus 7.5 over 2. Minus 4.5 minus 7.5 is minus 12 over 2. Minus 12 over 2 is minus 6. So according to the first solution for x is equals to minus 6. But we know that x is the length of line segment ED. So x is a length, and x as a length, it must be a positive number, it can never be equal to minus 6, that is a negative number. So the second solution, the first solution for x is the correct solution, so we cancel the solution, and we take into account only the second solution for x. The second solution for x is as follows. X equals to minus 4.5 plus 7.5 over 2. Minus 4.5 plus 7.5 is 3. So it is 3 over 2, the 3 halves, that is 1.5. So in total, we should find out that x equals to 1.5 units in its length. Our task is to find out the area of this region, that is the area of the green triangle ABC. The area of the green shape is equals to the area of the green triangle ABC. The area of this green triangle ABC equals to the base BC times the height edge over 2. And again, the area of the green triangle ABC equals to the base BC times the height edge over 2. The base BC is 1 plus x and the height edge is 3. BC is 1 plus x and the height edge is 3. Okay. So in total, the area of the green shape equals to x plus 1 times 3 over 2. X is 1.5. X is 1.5, therefore x plus 1 is 1.5 plus 1, that is 2.5. So the base BC equals to 2.5 times the height edge, that is 3 over 2. 2.5 times 3 is 7.5. So it is 7.5 over 2, and 7.5 over 2 is 3.75 square inches in size. So if you found out that the area of this green shape, that is the area that we are looking for in this question, is equals to 3.75 square inches in size. So we finish with the first method. In the next step, I repeat on the solution of the second method. A, B, C, D is right angle, therefore all those four angles are right angles. We define the length of line segment ED is x. So AD in total equals to 1 plus x. We also know that the opposite sides of a rectangle are equal to each other. So rectangle ABCD, sine AB equals to the opposite side DC. But AB is 3, therefore the opposite side DC must be also equal to 4 units in its length. Likewise, according to the symbol, with the same rectangle ABCD, side AD must be equal to the opposite side BC. but AD is 1 plus x, therefore the opposite BC must also equal to 1 plus x units in its length. In the next step we did the construction, that is to say from point D we do perpendicular on BC. So this angle equals to 90 degrees, this angle also equals to 90 degrees according to the construction. By doing this construction, we are the polygonal AB, ME. Inside polygonal AB, ME, we have 1, 2 third angles, and therefore this fourth angle must be equal to 90 degrees inside according to the rule that says that the sum of the angles in any polygonal is equal to 360 degrees. So in polygonal AB, ME, we have 4 angles, and therefore polygonal ABME is a rectangle. But you also know that the opposite sides of a rectangle are equal to each other. So in rectangle ABME, side AB must be equal to the opposite side ME. But AB is 3, therefore the opposite side ME must be also equal to 3 units in its length. In the next step, we define this angle AEB is theta, and we focus on the right upper triangle, line AEB. In the right upper triangle AEB, triangle theta equals to AB over AE. Again, the right upper triangle AEB, triangle theta equals to AB over AE. AB is 3 and AB is 3 and AE is 1. So in total AB equals to 3 over 1, that is 3. So according to equation 1, triangle theta equals to 3. And we have the trigonometric identity that says that tangent theta plus 45 degrees equals to 1 plus tangent theta over 1 minus tangent theta. We define this trigonometric identity as equation 2. But we already found out that tangent theta equals to 3, so we can substitute tangent theta this equation 2 by 3. We did it, we found out that tangent theta plus 45 degrees equals to 1 plus tangent theta, and tangent theta is 3. So it is 1 plus 3 over 1 minus tangent theta. So it is 1 minus 3. So total tangent theta plus 45 degrees equals to 1 plus 3, that is 4, over 1 minus 3, that is minus 2. 4 over minus 2 is minus 2. So in total we found out that according to equation 2, tangent theta plus 45 degrees, tangent theta plus 45 degrees equals to minus 2. Tangent theta plus 45 degrees equals to minus 2. This is according to equation 2. But according to equation 1, we only found out that tangent theta equals to 3. So in the next step, AD is one side of rectangle ABCD, therefore it is absolutely straight line. It's a side of rectangle, it is absolutely straight line. So if you focus on the right side of the straight line AD at point D, here the sum of the angles must be equal to 180 degrees according to all three. All three said that the sum of the angles on one side of the straight line is equal to 180 degrees. So which angles we have at the right side of the straight line AD at point D? We have this angle is equal to theta, plus this angle is equal to 45 degrees inside, plus this missing angle is angle DEC. In total, the sum of those two angles must be equal to 180 degrees according to all three. And again, in the right side of the straight line AD at point P, the sum of the angles must be equal to 180 degrees according to all three. So which angles we have at the right side of the straight line AD at point E? We have angle theta plus angle 45 degrees plus the missing third angle, that is actually angle DEC. In total must be equal to 180 degrees according to all three. If we subtract theta plus 45 degrees from this equation, we found out that the missing angle DEC equals to 180 degrees minus theta plus 45 degrees. So actually this is the missing angle DEC, this equals to 180 degrees minus theta plus 45 degrees. The next step, we focus on this right lower triangle, triangle EDC. In this right lower triangle, triangle EDC, triangle 180 degrees minus theta plus 45 degrees equals to DC over DE. And again, the right lower triangle DEC, or EDC, triangle 180 degrees minus theta plus 45 degrees equals to DC over ED. DC is 3 and ED is X. So in total, tangent theta minus 180 degrees minus theta plus 45 degrees equals to 3 over X. Again, tangent 180 degrees minus theta plus 45 degrees equals to 3 over X. You have another trigonometric identity. And again, according to equation 3, we should find out that tangent 180 degrees minus theta plus 45 degrees equals to 3 over X. This is equation 3. We have the trigonometric identity that says that tangent 180 degrees minus theta equals to minus tangent theta. So according to this trigonometric identity, we get that tangent 180 degrees minus theta plus 45 degrees equals to 1 sinus theta plus 45 degrees. Again, according to this trigonometric identity, sinus 100 degrees from theta plus 45 degrees equals to 1 sinus theta plus 45 degrees. So we can substitute sinus 180 degrees from theta plus 45 degrees by minus sinus theta plus 45 degrees, because those two expressions are identical according to this trigonometric identity. So we did it. So sinus 180 degrees from theta plus 45 degrees equals to minus sinus theta plus 45 degrees, and it equals to 3 over x. So according to equation 3, we found that minus sinus theta plus 45 degrees equals to 3 over x. But we already found out that according to equation 2, sinus theta plus 45 degrees equals to minus 2. So we can substitute sinus theta plus 45 degrees by minus 2. We did it. So in total, according to equation 3, we have here minus, so I copy the minus here. And we have sinus theta plus 45 degrees equals to minus 2 according to equation 2. So in total, on this side of the equation 3, we have minus 2. This equals to 3 over x. Minus 2 is plus 2, so 2 equals to 3 over x. 2 equals to 3 over x. Here we multiply this equation by x and find out that 2x equals to 3. Here we divide this equation 3 by 2 and find out that x equals to 3 halves, that is 1.5. This is the means in line 70 is equals to x, and it is equals to 1.5 units in its length. Our task is to find out the area of this green shape. The green shape, the green triangle ABC. Again, our task is to find out the green shape, but the green shape is actually the green triangle ABC. So our task is to find out the area of the green triangle ABC. The area of this green triangle ABC equals to the base BC times the height edge over 2. So again, the area of the green triangle ABC equals to the base BC times the height edge over 2. We only found out that BC equals to 1 plus x and the height edge equals to 3. Again, BC equals to 1 plus x and the height edge equals to 3 divided by 2. So in total, the area of the green shape equals to 1 plus x times 3 over 2. But the x is 1.5, so x plus 1 is 1.5 plus 1, that is 2.5. So BC equals to 1.5, the base BC is 1.5, times the height edge, that is 3 over 2. 2.5 times 3 is 7.5, and 7.5 over 2 is 3.75 square units in its size. So the area of the green shape equals to 3.75 square units in its size. So in both methods, we have found out that the area that we are looking for this question, that is the area of this green shape, equals to 3.75 square units in size. So we finish with the first question. In the next step, we repeat on the solution on the second question. In the second question, our task is to find out the radius of this semicircle. In the drawing, we have a rectangle ABCD. This is line 70P, this is equal to 2 units in its length. This is line 70QB, this is equal to 1 unit in its length. Again, ABCD is a rectangle. So this semicircle is inscribed by rectangle ABCD. And our task is to find out the radius of this semicircle that is inscribed by rectangle ABCD. So first of all, ABCD is a rectangle, therefore all those four angles are right angles. And we defined the point of tendency of tangent DC with this semicircle. This point is point M. Likewise, we defined the point of tendency of tangent BC with this semicircle. This point is point T. We defined the center of this semicircle. This point is point O. We also defined the radius of this semicircle as X. In the next step, we join points O and M together by straight line. Point O is the center of the semicircle, point M is the point of the semicircle itself, therefore OM is the radius of the semicircle equals to x according to our definition. The radius of M is equals to x, the radius of M is 1 to point M, that is the point of tendency DC with this semicircle. And whenever your radius is 1 to the point of tendency, then tangent DC will be perpendicular to the radius MO. If DC is perpendicular to MO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. So inside the small quadrilateral, so in the next step, we join the points O and T together by straight line. OT is of course the radius of this semicircle, that is equals to x. The radius of T is equals to x, the radius of T is 1 to point T, that is the point of tendency of tangent BC with this semicircle. And whenever your radius is 1 to point of tendency, then tangent BC will be perpendicular to the radius TO. If BC is perpendicular to the radius TO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to the sum rule 1. So in total, inside the lower small quadrilateral OTCM, we have 1, 2, 3 arteries. The sum of arteries is 270 degrees, so 270 degrees plus the size of this fourth circle, and total must become to 360 degrees, according to the rule that says that the sum of the angles in any quadrilateral is equal to 360 degrees. And therefore, this fourth circle must be equal to 90 degrees in size. So inside quadrilateral OTCM, we have 4 arteries, and therefore can relate to quadrilateral OTCM as a rectangle. But we also know that the opposite sides of a rectangle are equal to each other. So in the small rectangle OTCM, side OT must be equal to the opposite side MC. But OT is x, therefore the opposite side MC must be also equal to x units in its length. Likewise, according to the same rule, in the same small rectangle OTCM, side OM must be equal to the opposite side TC. But OM is x, therefore the opposite side TC must be also equal to x units in its length. So in total, we found out this quadrilateral OTCM is not a rectangle but a square. Why? Because of the fact that all of its sides are equal to each other, each side equals to x. In the next step, we did a construction, that is to say from point O, that is the center of this semicircle, we draw perpendicular on AD. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point O and AB. This point is point L. By doing this construction, we created the upper small quadrilateral LOTB. Inside this small quadrilateral LOTB, we have 1, 2, 3 arteries, and therefore this fourth circle must be equal to 90 degrees inside. So inside quadrilateral LBTO, we have 4 arteries, and therefore quadrilateral LBTO is a rectangle. You can write to quadrilateral LBTO is a rectangle because it has 4 rectangles. But you also know that the opposite sides of a rectangle are equal to each other. So in the small upper rectangle LBTO, side OT equals to the opposite side LB. But OT is x, therefore the opposite side LB must be also equal to x units in its length. What is the length of this short line of this line segment? LQ. LQ equals to LB minus QB. Again, LQ equals to LB minus QB. So LQ equals to LB, that is x, minus QB, that is 1. So in total, we found out that the missing line side LQ equals to x minus 1 units in its length. In the next step, we did another construction, that is to say, from point O, that is the center of this semicircle, we do perpendicular on AD. Again, from point O, that is the center of the semicircle, we do perpendicular on AD. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point O and side AD. This point is point Z. By doing this construction, we created quadrilateral LOZ. Inside quadrilateral LOZ, we have 1, 2, 3 arteries, and therefore this fourth circle must be equal to 90 degrees inside. And therefore, can relate to quadrilateral LOZ as a rectangle because it has 4 rectangles. By doing this construction, we created another quadrilateral, that is quadrilateral OZDM. Inside this quadrilateral OZDM, we have 1, 2, 3 rectangles, and therefore this fourth circle must be equal to 90 degrees inside. According to the rule, the sum of the angles in a quadrilateral is equal to 360 degrees. So inside the quadrilateral OZDM, we have 4 rectangles, and therefore can relate to quadrilateral OZDM as a rectangle. And again, we can relate to this quadrilateral OZDM as a rectangle because it has 4 rectangles. But we also know that the opposite sides of a rectangle are equal to each other. So in this rectangle OZDM, side OM must be equal to the opposite side ZD. but OM is x, therefore the opposite side ZD must be also equal to x units in its length. What is the length of this missing 97? 97 ZP. ZP equals to ZD minus PD. Again, ZP equals to ZD minus PD. So ZP in total equals to ZD, that is x, minus DP, that is 2. So in total, the missing 97 ZP equals to x minus 2 units in its length. So this is the big angle ZOT. The big angle ZOT equals to 90 degrees plus 90 degrees, that is 180 degrees. And again, the big angle ZOT equals to 180 degrees in its size. And we know that any angle that is also 180 degrees in its size is defined as a straight line. Therefore, line 7 ZOT is a straight line. Line 7 ZOT is a straight line. If ZOT is a straight line, then ZT is also a straight line. Here, ZT is also a straight line. And this is shape ABTZ. Shape ABTZ is 1, 2, 3, 4 sides. Shape ABTZ is 4 sides. And because of the fact that shape ABTZ has 4 sides, it is a quadrilateral. Shape ABTZ that has 4 sides, it is a quadrilateral. So inside this quadrilateral ABTZ, we have 1, 2, 3, 4 right angles. Quadrilateral ABTZ has 4 right angles, and therefore we can relate to this quadrilateral ABTZ as a rectangle. But you also know that the opposite sides of a rectangle are equal to each other. So in rectangle ABTZ, side AB must be equal to the opposite side ZT. The opposite sides of rectangle are parallel to each other. So in rectangle ABTZ, side AB is parallel to the opposite side ZT. And again, in rectangle ABTZ, the opposite sides are parallel to each other. That is to say, side AB is parallel to the opposite side ZT. AB is parallel to ZT, and the QP is defined as the transversal. That is to say, it cuts those two parallel sides at those 2 points. So all the requirements of rule 10 are satisfied, and therefore we can implement a rule 10. So repeat quickly rule 10. According to rule 10, corresponding angles between parallel lines are equal to each other. In the drawing we have line A that is parallel to line B. The red line C is transversal, that is to say it cuts those the two parallel lines A and B at those 2 points. Those 2 angles are defined as corresponding angles, and they are located between the parallel lines A and B. Therefore they must be equal to each other and their sizes. So if the size of this angle is 1, then the size of this angle must be also equal to 1, because they are equal to each other according to this rule, rule 10. Likewise, those 2 angles are also defined as corresponding angles, and they are located between the same parallel lines A and B. Therefore they must be equal to each other in their sizes. So if the size of this angle is 2, then the size of this angle must be equal to 2. Okay? Because they are equal to each other according to this rule, rule 10. So already mentioned before, all the requirements of rule 10 are satisfied in our drawing. Therefore we can implement a rule 10. Again, AB is parallel to ZT, and QP is the transversal that cuts those 2 parallels at points Q and point O. So all the requirements of rule 10 are satisfied, and therefore we can implement a rule 10. Those 2 angles are defined as corresponding angles, and they are located between the parallels AB and ZT, and therefore they must be equal to each other according to rule 10. According to rule 10, the set of corresponding angles between parallels are equal to each other. Those 2 angles are corresponding angles, and they are located between those 2 parallels AB and ZT, and therefore must be equal to each other in their sizes. So if the size of this angle is alpha, then the size of this angle must be also equal to alpha, because they are equal to each other according to rule 10. So in the upper right triangle L, O, and Q, this angle equals to alpha, this angle equals to 9 degrees, and this angle equals to 9 degrees, and therefore this angle must be equal to 9 degrees minus alpha. Why? Because 9 degrees minus alpha plus alpha is 9 degrees, and 9 degrees plus 9 degrees, it equals to 180 degrees, it is the sum of the angles in a triangle. Likewise, in the right triangle ZOP, this angle equals to alpha, this angle equals to 9 degrees, and therefore this angle must be equal to 9 degrees and minus alpha according to the sum rule that said that the sum of the angles in a triangle is equal to 180 degrees. In the next step, we prove that those two green right triangles can go into each other according to angle side angle rule. So why those two right triangles can go into each other? Right green triangles can go into each other. First of all, those two angles are both equal to alpha and therefore they are equal to each other. OQ is the radius of the circle is equal to x, and on the radius of the semicircle is equal to x. Likewise, OP is also the radius of the same semicircle is equal to x. So OQO equals to OP, they are both the area of the semicircle, is equal to x, and therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees minus alpha, and therefore they are equal to each other. So we should prove that those two right green triangles can go into each other according to angle side angle rule. So repeat again, we should prove that the green upper right triangle LQP congruent, this is the sign of congruent, to the right lower green triangle ZOP according to angle side angle rule. This is to say, we should prove that those two angles and the side that is included between those two angles, that is side OQ, in this upper right triangle LOQ corresponding equal to those two angles and the side that is included between those two angles, that is side OP of this right lower triangle, right lower green triangle ZOP. And therefore those two right green triangles can go into each other according to angle side angle rule. So in other words, we should prove that those two angles and the side that is included between those two angles in the upper right triangle LOQ corresponding equal to those two angles and the side that is included between those two angles of the right green triangle, right lower green triangle, or ZP. Therefore, those two right green triangles can go into each other according to angle side angle rule. And from the fact that those two right triangles can go into each other, we will derive that their corresponding sides must be also equal to each other and their lengths. According to the rule, it said that corresponding sides in congruent triangles are equal to each other. Those two triangles can go into each other, and therefore their corresponding sides, that is to say LQ and ZO, must be also equal to each other and their lengths. Why LQ is the corresponding side of ZO? Because of the fact that LQ and ZO are both located in front of this angle that is 90 degrees from the alpha, and therefore they are corresponding sides. So the corresponding side LQ equals to ZO. Okay, LQ equals to ZO, according to the rule that I mentioned. The corresponding sides, those two corresponding sides are equal to each other and the next. This is to say LQ equals to ZO. But we already found out that LQ equals to x minus 1. So we can write here that LQ equals to x minus 1. And from this equation, x minus 1 equals to LQ equals to ZO, we derive that ZO must be also equal to x minus 1 units in its length. This is the missing side ZO is equal to x minus 1 units in its length. We only found out that ZP equals to x minus 2, and the opposite OP of the green triangle or ZP equals to x. In the next step, we implemented the Pythagoras theorem on this right green lower triangle or ZP. According to the Pythagoras theorem, on this green right triangle or ZP, OP squared, that is the square of the hypotenuse, equals to OZ squared plus ZP squared. And again, this right lower green triangle or ZP, OP squared, that is the square of the hypotenuse, equals to ZP squared plus ZO squared. OP is x, therefore OP squared is x squared, and it is equals to ZO squared. ZO is x minus 1, therefore ZO squared is x minus 1 squared, plus ZP squared. ZP is x minus 2, therefore ZP squared is x minus 2 squared. So in total, we should find out that x squared equals to x minus 2 squared, plus x squared equals to x minus 2 squared, plus x minus 1 squared. We open the brackets on this side of this equation and finally found out that x squared equals to x minus 2 squared. X minus 2 squared equals to x squared, plus 2 squared, that is 4, minus 2 times x times 2, that is minus 4x, plus x minus 1 squared. X minus 1 squared equals to x squared, plus 1 squared, that is 1, minus 2 times x times 1, that is minus 2x. Here we have x squared on both sides of this equation, so x squared again cancelled, after we can set x squared on this side of the equation we left with nothing, that is to say 0, while on the other side of the equation we have 4 plus 1, that is 5, minus 4x minus 2x is minus 6x, plus x squared. So in total, if you want to know that x squared minus 6x plus 5 equals to 0. So this is a quadratic equation. The general formula for quadratic equation is as follows: ax squared plus bx plus c equals to 0. In this general formula, a, b, and c are the coefficients of this quadratic equation, and x is the variable that we are looking for. And we find out the value of x according to the following formula. x equals to minus b plus minus square root of b squared minus 4 times a times c. In our specific quadratic equation, that is to say x squared minus 6x plus 5 equals to 0, the variable that we are looking for is x. And x is the radius of this semicircle. The coefficient a equals to 1, the coefficient b equals to minus 6, and the coefficient c equals to 5. So we have all the data that is needed in order to find out the variable that we are looking for. This one, our specific quadratic equation x, that is the radius of the semicircle. We just have to put the data of our specific quadratic equation inside this general formula for x. This way we find out the value of the radius of x, because x must have two solutions. So actually did it, we found out that x equals to minus b. b is minus 6, therefore minus b is minus 6, that is plus 6, plus minus square root of b squared. b is minus 6, so b squared is minus 6 squared, that is 36. Minus 4 times a times c, so it is minus 4 times a is 1, so minus 4 times 1 is minus 4 times c is 5, so minus 4 times 5 is minus 20. So in total minus 4 times a times c is minus 20, so inside the root we have 36 minus 20 over 2a. So a is 1, so 2a is 2 times 1, that is 2. So in total we should find out that x equals to 6 plus minus 36 minus 20 is 16, so inside the root we left only with 16 over 2. So x equals to 6 plus minus, x equals to 6 plus minus, the square root of 16 is 4 over 2. So x equals to 6 plus minus 4 over 2. So here we have two solutions that are possible for x. The first solution for x is as follows. X equals to 6 plus 4 over 2. 6 plus 4 is 10 and 10 over 2 is 5. So total, we found out that according to the first solution for x, the radius x of this semicircle equals to 5 units in its length. We have another solution for x. The other solution for x is as follows. X equals to 6 minus 4 over 2. 6 minus 4 is 2 and 2 over 2 is 1. So according to the first and the second solution for x, the radius x of this semicircle equals to 1 unit in its length. But it is impossible that x equals to 1. Why? Because of the fact that zp equals to x minus 2. Zp equals to x minus 2. If x equals to 5, then 5 minus 2 is 3, that is a positive number. It is definitely possible that zp equals to 3, that is a positive number. Well, if x equals to 1, then x minus 2 is 1 minus 2, that is minus 1. So zp is a left, and zp is a left, it must be a positive number, and minus 1 is a negative number. So that is the first reason that x can never be equal to 1. The second reason that x can never be equal to 1 because of the fact that the length of this side is zp equals to x minus 2. So zp is the left, so it's a left, it must be a positive number. That is to say, it must be greater than 0. So x minus 2 must be greater than 0. We added 2 to this inequality and finally found out that x must be greater than 2. X is greater than 2. If x is greater than 2, x can never be equal to 1, that is less than 2. So we have two reasons that x can never be equal to 1. Therefore, the only solution to this question is that the radius of this semicircle x, that is the radius that we are looking for this question, is equal to 5 units in its length. Okay, thank you very much.